Hi everybody, welcome to our third set of videos. What we're going to do with this set is we're going to sort of wrap up some ideas related to entropy, and then we're going to delve into some details regarding free energy. This first slide here we've all seen in class already, but I want to go through it real quick to review it. Let's not forget that we're talking about the most important equation ever, delta G equals delta H minus T delta S. So this equation essentially dictates what can happen and what can't happen. So in our first case with H negative and S positive, the G comes out to be negative. Is it spontaneous? Yes, and it will be spontaneous at all temperatures. The bottom case, a positive H and a negative S, gives us a positive delta G, no choice but to be positive. Is it spontaneous? No. In fact, there's nothing you can do about it. It will never be spontaneous. Then the middle two cases, the negative, negative, positive, positive, the delta G's are undetermined with those signs. It ultimately comes down to the question of temperature. In the minus minus case, you want to de-emphasize temperature because you want this negative enthalpy to carry the day. So you can make it spontaneous at low temperature. In the positive case, you want to emphasize the temperature term so that the positive entropy dominates. Thus, you can get the reaction to be spontaneous at high temperature. So this is really sort of the summary of spontaneity. What we're going to do for the rest of this presentation is talk a little bit more about entropy and the third law of thermodynamics, and get into some specific ways of dealing with instances of free energy. So, the third law of thermodynamics. During the first slam, you may have noticed in the back of the book, when you looked up some numbers, the entropies are tabulated not as a delta S0, but as simply S0. And we'll get into the zero part later, but right now I want to talk about why there's no delta there. The reason there's no delta there is because of the third law of thermodynamics, which essentially says that the entropies listed in the back of the book really are delta entropies. They are changes in entropy, but they are changes from an idealized situation. Namely, we're talking about the entropy of that material as it is presently stated if it were to have started as a perfect crystal at 0 Kelvin. So by definition, a substance that is at 0 Kelvin and is a perfect crystal means there are no imperfections. Every atom is exactly where it should be in the unit cell. Every molecule is lined up perfectly within the unit cell. This is not a reasonable situation in real cases. There are always going to be some minor imperfections and deformations within a crystal. But if you can get to the ideal, everything's exactly where it should be, and you're at 0 Kelvin, so the wiggles and jiggles of the system are at a minimum, well then you are at the lowest entropy point possible. So that would be an entropy of 0. But when you look these numbers up, you're going to see simply S's. But that's because they're really a change in entropy from this idealized state. So let's take a quick look at a small part of the chart that you could look up in the appendix. I have here bromine liquid and bromine gas. Now, of these 6 empty squares that I show you right now, you might actually be able to predict the values of 2 out of the 6 squares. You might remember that delta HF0, the heat of formation for bromine liquid, is going to be 0. And why is that? Because Mommy Nature, when we ask her for bromine, what she gives us at standard state conditions is she gives us Br2 in the liquid state. In other words, you don't have to put any heat in or out of a system to get your hands on bromine under standard state conditions. It's already Br2 liquid. Likewise, the free energy of formation for bromine liquid will also be 0. One way to think about free energy, we'll get into this later on, is to think about it as being work. So if you don't have to do anything, if you don't have to do any work, then the free energy of formation for that material would also be 0. Okay, the other numbers are not going to be 0. Here they are. For Br2 liquid, the entropy is 152. Notice also the change in the units, joules versus kilojoules for H and G. It's just because of a scale factor, entropy changes are smaller than free energy and enthalpy changes. So 152. The delta H of Br2 gas. Now, Br2 gas is not the standard state. If you get bromine at 25 degrees and 1 atm, it's actually going to be a liquid. So to turn it into a gas, what would you have to do to turn a liquid into a gas? You would have to heat it up. So the enthalpy of formation is, unsurprisingly, north, more positive than the heat of formation of bromine liquid. So 31 kilojoules per mole. Likewise, you have to put in some work to get bromine gas, so it has a positive positive free energy of formation. And now the entropy. The number I'm going to put in this sixth and final square, think about this for a second, what should it be larger than? It should be larger than the entropy of the bromine liquid, because if I'm now talking about bromine gas, it should have a higher entropy. And sure enough it does, 245. So we should be able to make some relative sense out of all the numbers that you see in the appendix for enthalpy, free energy, and entropy. We should be able to know when we have zeros in the chart, when we have the standard state of the material, that's when we should be seeing zeros for free energy and enthalpies of formation. But all of the other numbers, maybe we can't predict their absolute value, their actual value, but we should be able to understand why one number is 152 and the other number is 245. You should be able to have a relative understanding of the numbers in the back of the book, in the appendix here. Okay, so let's detail about free energy. Just as there are a number of ways to calculate entropy, there are a number of different ways to calculate free energies. Here's our first way of calculating free energy. It is reliant on the most important equation ever. You can get the free energy of a system if you know its enthalpy change, and you subtract from that the temperature times the entropy change. So delta H minus T delta S, so equation we've seen plenty of times. Now, in this problem here, I've given you the values you would find in the back of the book for the enthalpies of formation for our reactants and our product, and I've given you the standard entropies for those reactants and products. Now, before I do this problem, before I start solving for the delta H and the delta S, what do I need to do? If you said balance the equation, give yourself a pat on the back. If you look in the equation, there are no coefficients. That is a telltale sign that it's not balanced. To balance it, we'd need a 2, a 1, and a 2. Okay, so now we can go ahead and calculate the delta H. We would do a products minus reactants calculation for each of the delta H and the S. You should take the time to make sure that for the delta H, you would get a value of negative 198 kilojoules, and for the delta S, a value of negative 187 joules per Kelvin. You'll notice the mole bit in the units has been factored out because we need to multiply each of the enthalpies and the entropies by the number of moles in the balanced equation. So my delta H and delta S values are mole-free, so to speak. So then my delta G here, there's one silly mistake you can make at this point. We need to make sure that we convert either our kilojoules to joules or our joules to kilojoules. I'm going to go ahead and convert the kilojoules to joules for the delta H and do the rest of the calculation. And then to save a little space, I'm going to put my final answer here in kilojoules. So I have a free energy change of negative 142 kilojoules. Now, what does that tell me about the reaction? I now know that this reaction is spontaneous. Okay, this reaction will happen. What we really have here is the combustion of sulfur dioxide. And combustion reactions are spontaneous reactions. They will happen. We have here a situation now. Let's look at the sign. The delta H was negative. The delta S was negative. So under what conditions are a negative-negative combination spontaneous? They are spontaneous at low T. So apparently 298 is low enough. So this reaction would be spontaneous so long as we kept the temperature low enough for this system. All right, so that is one way to calculate free energy. Another way to calculate free energy. I'm going to try to find the free energy for this reaction given these other two reactions. Now this should sound really familiar. We're going to combine the given reactions to find the find reaction. Does this sound familiar? Have you done this before with delta H? Say it. What does it sound like? Yep, it is Hess's law. Okay? So what we need to do is manipulate the given equations so that when we add them together, we'll get the target equation. And what I think I need to do is, and you should follow along here, see if this is right, I need to flip the top equation, which would cause me to flip the sign of the delta G, and I need to take the second equation and multiply it by 2, which means then I would multiply the delta G of that equation by 2. So when we put it all together, the delta G of my target equation is going to be equal to 1088, the flipped sign for the first equation, plus a negative 1602, 2 times negative 801, to get a negative 514 kilojoules. All right, so what does that tell me about this reaction? It's spontaneous. Not surprising because we have yet another combustion reaction. Okay, combustion reactions really want to happen. Okay, so we have here a spontaneous reaction. So that's the second way to calculate delta G. Here is way number 3 of calculating delta G. This is the exact same algorithm that we have available to us to calculate delta H or delta S. It is another products minus reactants calculation, where you look up the free energies of formation in the appendix, multiply by the number of moles in the balanced equation, and again, products minus reactants. All right, so that gives us 3 ways to calculate delta G. As we go through the rest of the unit, we're going to see a couple of other ways to get delta G, but right now we have 3 different ways to get delta G. We can get it from H minus TS, we can get it from Hess's law, and we can get it from products minus reactants. And the method you use is all dependent upon the information you're given to start your particular problem. Are you given free energies of formation? Products minus reactants. Are you given some equations to manipulate to find a new equation? Use Hess's law. Are you given enough information to find the enthalpy and entropy changes at a given temperature? Then use G equals H minus TS. All right, one last thing to do here with free energy. We're going to now actually apply a concept of free energy to do a fairly straightforward problem. This is identical to a problem that you did on the SLAM, so I'm just reaffirming here something that you already should have done, and that is we're going to find the boiling point for liquid bromine. Now, boiling point. What you need to remember about boiling point is that the boiling point is actually an equilibrium condition. When something boils, it is at equilibrium, of course, between the liquid and the gas phase. So we have liquid molecules going into the gas phase and gas molecules coming back into the liquid. So if this is at equilibrium, then you will recall then that the delta G must be equal to 0. When something's at equilibrium, it does not have a net effect on the universe. And remember that delta G is equal to negative T times delta S. So there's no entropy change when we are at equilibrium. So we can use this fact than to solve for the equilibrium temperature, or in this case the boiling point temperature. That's simply going to be taking delta G, which is going to be equal to 0, set that equal to delta H minus T delta S. So to find my temperature, I have to do delta H divided by delta S. Now take a quick second here. What's going to be the goofy mistake you can make here? We have kilojoules in the delta H, we have joules in the delta S. Switch one to the other. So I will go with 31,000 joules divided by 93 joules per Kelvin. And I'm going to get a temperature of 333, that's in Kelvin, which is equal to about 60 degrees Celsius. So bromine boils at about 60 degrees Celsius, which isn't all that terribly high. Bromine has a pretty high vapor pressure, so that relatively low boiling point does make some sense. So here we're not doing so much of a delta G calculation as we are taking a delta G concept, namely that of equilibrium, and using that to do a calculation for an equilibrium temperature. Okay, so that's where things stand now. We now know a lot more about delta G. What we'll be doing in class is we're going to be talking about solving delta G problems when we are not necessarily under standard state conditions. So far, everything's been done assuming that we are at 1 atm. Well, we're not always going to be at 1 atm. What do we do about that case? We'll talk about that in class over the next couple of days.